Okay, so this is going to be me going through the 2025 Unit 3 Pure Maths. Just make sure that you've got a calculator and a formula booklet with you before we get started. And let's get cracking with the first question. Okay, question number 1, part A. Nice, easy start to this question. So we're going to differentiate that. So dy dx, that means the derivative with respect to x of whatever we're about to put in this set of brackets, and I need a double set of brackets. So the derivative of that thing with respect to x. Now remember that we've got the chain rule going on here, so we're going to multiply by the power. We're going to have our exact same original bracket, but with a 1 smaller power. And then the bit that lots of people forget is we're going to have to multiply by the derivative of the inside. Now the derivative of e to the minus x is minus e to the minus x, sorry, and then the derivative of x squared is 2x. Now it's always worthwhile in questions like this to check whether they want you to simplify or not. So it just says differentiate, so I know I don't need to go any further. Even if I did, there's not really much I can do. Okay, so I'm going to move on to part B. This one, so it looks like I got the product of two functions of x, so the derivative of e to the 2x sine 3x. And just a reminder, if you've got a function uv and you differentiate it, well, that is u dash v plus v dash u. So differentiate the first one, multiply by the second one. So 2e to the 2x times sine of 3x, and then you add that to differentiate the derivative of the second one, multiplied by the first one. So the derivative of sine 3x is 3 cos 3x. So we're going to have 3e to the 2x cos 3x. Now, even though it doesn't ask me to, I was brought up to always simplify where I could. Both of these have a factor of e to the 2x, so I have 2 sine 3x plus 3 cos 3x. Okay, and remember, we're doing differentiation here, so no need for any constants of integration. Okay, lots of people put them on, but we don't want to see those here. Okay, moving on. As you might expect, after seeing a question with a chain rule and then a question with a product rule, we've now got a question where we're going to use the quotient rule. So the derivative of cos of 2x over x squared plus 1. And just a reminder, if you've got a function like u over v, where u and v are functions of whatever variable, if you differentiate with respect to that variable, you differentiate the top, multiply by the bottom, subtract the derivative of the bottom times the top, all over the bottom squared. Okay, so differentiate the top, that'll give us minus 2 sine 2x, and when we multiply it by the bottom, we're going to get that. Then we're going to subtract from that the derivative of the bottom times the top, so the derivative of the bottom is 2x, multiplied by the top is cos of 2x, and that's all going to be over the bottom, x squared plus 1, all squared. And there's not really too much in terms of tidying up that we can do with that one, so I'm just going to leave it. Oops, bad underline, but there we are. The functions you want to be on the lookout for in situations like this are exponential functions. Like, they generally mean that there's going to be some tidying up that you can do. Okay, on to part B. We've got an implicitly defined function, so we're going to go through it and we're going to differentiate everything, every term, each side, with respect to x. So we're going to get 2. And then we've got a function, we've got two functions multiplied together here. We've got minus 3x squared and y cubed. So we're going to use the product rule. So we're going to differentiate minus 3x squared, which is going to give us minus 6x multiplied by y cubed, and I have not differentiated the y function there. Okay, my next term then is what I get when I differentiate the y cubed. So I'm going to get 3y squared dy by dx. So this term then is going to be minus 3x squared times 3y squared dy by dx. So I'm going to get minus 9x squared y squared dy by dx. And then the right hand side is going to give me 0. Okay, so if I tidy this up, I can get 9x y squared dy by dx, and then that's going to be equal to 6xy cubed minus 2. And then to make dy by dx the subject, I'm just going to divide through by that 9x squared y squared. So 6xy cubed minus 2, apologies, over 9x squared y squared. If you were to write the answer that's equivalent to this, but where all the signs are the opposite, so minus 6xy cubed plus 2 over the negative of the bottom, that's absolutely fine. There's nothing wrong with that at all. Okay, moving on. So here we have one of the lovely 6-mark questions that come up in an awful lot of papers. The thing that I've got to tell you to be aware of, because the first time I did this question, I ignored it, is this bit here. I want my answers in radians, so don't give your answers in degrees. You'd be amazed, even though it says it there in blue and it says give your answers in terms of pi, you'd be amazed by how many people left their answers in degrees. And I'll put my hand up and say I'm definitely one of them. Okay, so cos 2x plus sine of x. Now, immediately this should make you think of double angle cos. And remember, double angle cos is the one where there's 3 different variations of it. So we need to think cos 2x. We want it to be something in terms of sine. So we're going to go ahead and use 1 minus 2 sine squared of x. If you try and use the one with cos squared in, you'll have to do another substitution. And if you use the one with both sine squared and cos squared in, you'll have to do another substitution. So this is the quickest one. So this equation then turns into 1 minus 2 sine squared of x plus sine of x equals 0. Let's make the quadratic term positive. So 2 sine squared of x minus sine of x minus 1 equals 0. I'm going to attempt to factorize that because it looks pretty factorizable. So I'm definitely going to have a 1 and a 1, and I need a 2 sine x and a sine x. And then I've got some negatives to put, and I know if I do 2 sine x times minus 1, and then 1 times sine x, positive 1 times sine x, I'll get that middle term that I need. Okay, so I can go ahead now and solve for sine x for both of these. So I'm going to set the first bracket equal to 0, which will lead me to sine x being equal to minus a half, and the second bracket equal to 0 will lead me to sine x being equal to 1. If I apply arc sine or inverse sine or shift sine, whatever you want to call it, to each of these, well, this first one, when I do inverse sine of minus a half, well, what am I going to get? I'm going to get 7 pi by 6. Okay, so this is equivalent to 210 in the degrees world. And then I'm also going to get 11 pi by 6. Now, it's entirely up to you how you find these alternate solutions. You may use the cast diagram if you insist. Personally, I've always used the graphs because I just think they're better to use because you need to use them. You need to know how to use them anyway. So you need to know how to draw them, I should say. So you may as well learn how to use them to find these alternate solutions. Okay, so there's 2. I don't need to do any more because it says between 0 and 2 pi, and 11 pi by 6 is nearly 2 pi. And then my other solution is going to be inverse sine of 1. And if you think about your sine graph, that is going to give you pi by 2. And there is only that one value. there between 0 and 2 pi radians. And so there we are, always a gift of a 6 marker, as long as you read the bits in blue, which, as I said, I may have forgotten once or twice. Moving on to the next question. Another solving equations question. And so we've got to think here, well, we're not going to use the same identity as we did before, but we're going to use the one that links sec squared and tan squared. So you should hopefully remember that sec squared of theta is identical to 1 plus tan squared of theta. So I'm going to use that substitution in here. So I'm going to have two lots of 1 plus tan squared of theta minus 5 minus tan theta equals 0. So if I expand those brackets and collect like terms, so I'm going to get two lots of tan squared theta minus tan theta, and then I'm going to have minus 5 plus 2, so minus 3 equals 0. Now, I'd like to think this one factorizes again. Yes, it does. So I know I'm going to have a 3 here and a 1 here. And I know if I put a tan theta in here, it'll give me 3 tan theta. And if I put a 2 tan theta in here, I'll get a 2 tan theta. So I'll make that one negative and that one positive. So then if I do the same again, put each individual bracket equal to 0, I'll get these two branches of solutions to consider. So tan theta equals minus 1 and tan theta equals 3 over 2 or 1.5. Inverse tan to both sides. So we're going to have theta equals inverse tan, and I didn't actually pay attention. Am I in degrees or radians? Degrees. Okay, don't do what I did. I saw this question and I just went off on autopilot. I didn't read any of the details, which is how you make mistakes. So inverse tan of minus 1, I'd like to think most people know this one. You're going to get 135 degrees, and then you're going to add 180 degrees to get you 315. Okay, if you don't know that one, might be worth remembering tan of 1 and tan of minus 1. The first one's 45, the second one is 135. Then if we do inverse tan of 1.5, this is one that I'm not going to pretend I know, I just know it's greater than 45. And when you put it into your calculator, you get 56.31 degrees. And then the next one after that on the next wave, if you add 180 degrees, you're going to get 236.31. So another fairly generous, I'll be honest, I always think these questions are generously marked. Another 6 marks. So we've just got 10 marks, which is 10% of the paper, by doing two very simple questions. Okay, so these are always ones I'd recommend you make sure you can do as part of your revision because they're very generously marked. Moving on. Some small angle approximations here. And in case you don't know how I got there, the fact it's saying theta is small tells me that I'm going to be using my small angle approximations. So if we just have a recap, sine theta is approximately equal to theta, and cos theta is approximately equal to 1 minus theta squared over 2. Now, these work when theta, so modulus of theta is very, very small, much, much less than 1. The smaller they are, the better the approximations. I'm sure you've seen the graphs that show you how accurate these approximations are. Okay, so then we're going to sub those into our given function. So I'm going to have 1 minus theta squared over 2. Now I know students don't generally like fractions on top of fractions. For some reason I can't draw this part of the line there. And then 1 plus, well, if sine theta is approximately equal to theta, then sine 2 theta is approximately equal to 2 theta. And I've got that equal to 0.8. So I'm going to multiply through by the 1 plus 2 theta. So 1 minus theta squared over 2 equals 0.8 plus 1.6 theta. And there I've got yet another quadratic. It feels like this is all we're doing so far, this paper. I'm going to multiply through by 2. So 2 minus theta squared equals 1.6 plus 3.2 theta. Make the theta squared positive. So theta squared plus 3.2 theta minus 0.4. Now this one feels like it's factorizable as well. Maybe I'm wrong. Yeah, I think actually I'm wrong. I was thinking about like 0.8 to 0.4, but then that doesn't work. So I'm not going to spend really any time on it at all. I'm going to go straight into using the quadratic formula. So it's minus b plus or minus the square root of b squared minus 4 times 1 times minus 0.4. So I'm going to put that in there, times 1 times 0.4. Okay, if you want to put the double negatives, that's fine. I choose not to, over 2a. Okay, and that is what you need to show. At the very minimum, that is what you need to show. My two solutions then, if I do them separately or if I use the solve an equation function on my calculator, I'm going to get, so I'm just checking the question for the accuracy, doesn't matter. So I'm going to go to 3 decimal places here, I think. 0.120, because then there's a 4 after that 0. And then theta is also equal to minus 3.320 to 3 dp. Okay. Now there's one of those that I certainly wouldn't categorize as small. Okay, which is this one. Okay, and the giveaway here, if you look at the question, the solution. We're not looking for multiple solutions. So here, let's explain why. Since theta is small, we know that we need 0. Let's get rid of the 0. Let's just do that. Okay, and then another quite nice, I think, 6 marks from a trig question. So it's 18 marks on the bounce coming from trig, which is nice if you like trig, not if you don't. Okay, moving on. Okay, trapezium rule. So another trapezium rule, sorry. Another what could be quite straightforward 4 marks here. This is a method that's just really important that you learn. I know you've got calculators. I know you can find the answer to these things exactly, but we just have to do it. So I've always set mine out as a bit of a table. So I would have my x and my y, and then I'd have my my sort of subscript. So the first one is going to be x0, x1, 2, 3, and 4. So my first x value is going to be 0. My final x value is going to be pi by 3. And so we need to think, how do I get from 0 to pi by 3 in 1, 2, 3, 4 jumps? Okay, so I'm first of all going to calculate h, which is pi by 3, divided by 4, which is pi by 12. Okay, so I'm going to go up in pi by 12s each time. So pi by 12, 2 pi by 12, which is pi by 6, 3 pi by 12, which is pi by 4, and 4 pi by 12, which is pi by 3. Then to find my y ordinate, I'm going to use those values, 0, pi by 12, etc., and I'm going to put them into my function, my sec squared function. So sec squared of 0 is 1. When you then do sec squared of pi by 12, I'm fancy, so I'm going to write them in surd form where I possibly can. Then for the next one, we get 4/3. Then for the next one, we get 2. And for the next one, we get 4. Okay, so our x ordinates now are pretty much done with. So what we're looking at in the table, the things we're going to use from here on in are these ones. So remember, for the trapezium rule, It's the first one plus the last one, and then double the sum of all the ones in the middle, because if you remember where this comes from, these come from the length of the parallel sides of trapezia. The very left-hand most one is only in the first trapezium, the very right-hand most one is only in the final trapezium. All of the others are the left-hand side of one trapezium and the right-hand side of another, so we double counting them. Okay, so we have that the area, which remember is equal to this integral, and this integral, by the way, is one that's a little bit difficult for us to do, which is why we're using the trapezium rule to do it. And this is then approximately equal to h over 2, so pi by 12 over 2. You can straight away put pi by 24 if you prefer. Then I like a big set of square brackets. I've got the first one plus the last one. Okay, and then plus 2 lots of the sum of everything in between. So plus 4/3 plus 2. And if you notice, I've done, apart from calculating the y values, I haven't had to do anything laborious on my calculator yet. And I'm just going to put that into my calculator straight away, and the next answer I'm going to write down is the final answer, which is going to give me the fourth and final mark. I think I should probably have earned 3 of them by this point, but then when I look back at the question, and this is really important, I've got to stop rushing. I want my answer to 3 decimal places. When I write this answer down now, 808 to 3 decimal places, that is my 4th mark. Okay, so these questions, I do appreciate you might find them tedious. I know I certainly do, but there's a lot of marks for them, so it's well worth setting out everything nicely and properly. Okay, moving on. Then we've got a nice hence question. Now, I quite like these because they require thought. That is almost certainly the reason why a lot of students don't like these questions. They're not doing them they're not giving you questions that are super difficult and you can't do, but you will have to think, okay? And the integrand here that they've given you is definitely going to have something to do with the previous integrand, which remember was sec squared. So we've got to think to ourselves, well, what can we do with tan squared of x plus 2 to get it in terms of sec squared? And if you think back to our trig question that we just did, we saw that sec squared was 1 plus tan squared, which means tan squared is sec squared minus 1. So I can rewrite this as sec squared of x minus 1 plus 2, which is identical to sec squared of x plus 1, which means that integral is the integral between 0 and pi by 3 of sec squared of x dx plus the integral between 0 and pi by 3 of 1 with respect to x, sorry. And we know what this first bit is here. We know what this thing is because we've just worked it out. So this thing then is approximately equal to 808. And then the integral of 1 between 0 and 3, 0 and pi by 3, sorry, we'll want to integrate that. I'm going to get x, and then I'm going to evaluate x between 0 and pi by 3, which is just going to give me pi by 3. Okay, and then we are going to want to simplify that. So pi by 3 is about 1, so this is going to be about 2.8. When you put it into your calculator, you find it's 2.855. Okay, and I've gone to the same level of accuracy there that I did in the previous question. I wouldn't want to go to any more. Okay, so initially looking at it might look like quite a difficult question, but if you just think about it and apply all of this stuff up here that you know about trig, you can turn it into something that looks an awful lot more familiar and a little bit easier for you to deal with. Okay, moving on. This question here should bring positive memories back for you from Unit 1. Find the coordinates of the stationary point. Now, my spidey senses are going off here because the thing that's different about Unit 3 when compared with Unit 1 is we can now have points of inflection, and there's a bit of a giveaway in the question here, the stationary point. Now, something you may or may not know is with a cubic, if it has a maximum, then it must have a minimum as well. So that would then lead us to the wording stationary points. So this is leading me to think straight away that because there's only one, it's going to be a point of inflection. So I've got a little bit of a heads up of where I'm going there. Max and mins, when it comes to cubics, always come in pairs. You can't have a max without a min. So given the fact there's only one stationary point here, I'm 100% sure that it's going to be a point of inflection. But let's prove that. So f dash of x is equal to, so we multiply by the power, take one off the power. Multiply by the power, take one off the power. Multiply by the power, take one off the power. So there is my gradient function. We know at a stationary point, f dash of x is equal to 0. This tells us that 3x squared minus 12x plus 12 equals 0. I'm going to choose to divide through by 3 to make the numbers a little bit smaller. I'm going to leave the power as a squared, otherwise it'd be a bit difficult. Minus 4x plus 4 equals 0. Now, remember, there is only one stationary point here, so we're only expecting one solution. And actually, that is because that thing there is a perfect square. And that tells me that the x ordinate of my stationary point is 2. And it does ask for the co-ordinates here. So I do need to go ahead and find the y value. So f of 2 equals, I'm going to have 8 minus 24, which is minus 16, plus 24, which is 8, minus 5, which is 3. Obviously, you can use calculators if you want to do that bit. And up to there, we've probably got about 4 of the marks, certainly 3, probably 4. And I like to do a little mid-question summary. Therefore, the stationary point is at the coordinate 2, 3. So I now know where it is. I'm also fairly certain I know what it is. But let's go ahead and prove that. You've got a variety of different tests here. You can use the first derivative test, the second derivative test, the third derivative test if you really want, or the y value test. So it's really take your pick. Personally, I was always taught and have always liked the second derivative test, even though in this case it probably is going to be a less efficient way of doing it. But stick to what you know. So f double dash of 2, I'm going to get 12 minus 12, which is 0. Now, a second derivative of 0 is inconclusive. It doesn't actually show you anything. What it does lead you to believe is that there might be a point of inflection there, but it certainly doesn't tell you for definite that there is. So I'm going to have to go a little bit further. I'm going to have to look either side of it. So when x is 2, when x is 3, and when x is 1, I'm going to look at the second derivative. And I know that if there is a point of inflection there, I will have a change of what's called concavity. I'll have a change of sign of the second derivative. So when x is 1, I'm going to have 6 minus 12, which is minus 6. When x is 3, I'm going to get 18 minus 12, which is 6. Okay, and so what I would say is, since there is a change in concavity, x equals 2 is a point of inflection. Okay, now I've seen some spellings around where inflection has got an X in it. If that's what makes you happy, put an X in it, but that's how I was always taught to spell point of inflection. Okay, so let's just underline the important things that we found. We found where it is, and we found that it's a point of inflection. Okay, yeah, the first derivative test will work, and so will the y value test, if that's what you prefer to do. Okay, moving on. We had a little bit more room if we wanted to, but we didn't need it. Determine the range of values of x where the curve is convex. So you need to make sure that you remember the definition of what convex means. And just a little bit of a word of warning, unless it's been changed, unless it's been edited in future editions, the WJEC textbook actually has this the wrong way round, I believe. Okay, so just make sure that you're using the right definition here. The second derivative being greater than 0 means convex. Oops, means convex. Okay, so if you are working pretty much exclusively with the WJEC textbook, just make sure that you know that you're not using this one the wrong way around, and hopefully it has been fixed in future editions. Okay, so we have our second derivative from before, don't we? We had 6x minus 12. We want to set that equal to 0, which means 6x is greater than 12, which means x is greater than 2. And we actually knew that from before because we knew there was that 2 was the critical point. It was the point at which the concavity changed. So we knew the answer to this was either going to be greater than 2 or less than 2. Okay, if you wanted to write it using a different notation, you could write it like that, because you could be asked to write it using a specific notation. I prefer the inequalities myself, but you never know what you're going to be asked in an exam. Okay, and so we'll move on to question 6. Okay, another numerical methods question here, which is always lovely. So we've got an iterative formula there. Remember, that just means that you put a number in, you get an answer out, you take that answer, put it back in, spits another answer out, and you go around in this loop, hopefully making better and better approximations to the actual answer. So we know that x naught is 0.62, so that's going to be the first number we put in. So we know that x1, which is the next iterate, is what we get when we do 1/3 of e to the previous answer, so 0.62, and that is approximately, how approximately do I want it? Give your answer to 3 decimal places, so I'm actually going to write it a bit more accurately than that. 61964, I think that's plenty, which is equal to then 3 decimal places, 620. X2 then is what we get when we stick that number back in again, but I would always put the more accurate one in. If you've set up your calculator correctly, so if you've defined the function and used the x sub n as the answer key, you can actually get this to do it just by pressing equals over and over and over again, and it'll give you successive iterates. So if you put the more accurate answer back in, you're then going to get 0.61942, and then there's a 1, which is, that's approximately equal to, which to 3 decimal places is 0.619. So you can see there is a bit of a change there. And then x3, because it has asked for us to go as far as x3, when I put that in, I then get something that is the same, or very, very close anyway. What we've got 284. So once you get to the 4th, 5th, and 6th decimal places, they are different, but to the 3 that we want, they are the same. So there's my 3 answers. And we'll move on to part B, which I strongly suspect is going to be Newton-Raphson. And there we are. Yeah, Newton-Raphson. So 3 parts to this. So we'll start with dotty 1. Take an f of x as that and start with x naught as 1.5. So remember, for Newton-Raphson, you need the function, you need the derivative as well, and you need a point to start. So if that's our function, we also need the derivative of that, which is e to the x minus 3, which means we can now set up the iterative formula. And for Newton-Raphson, the next iterate is the current iterate minus the the function over the gradient. So e to the power of x sub n minus 3x sub n over e to the x sub n minus 3, which means x1 is equal to, well, we're going to replace all of the xn's with 1.5. So you should see that it is 1.512358, and that's more than enough. And they actually only want it to 3 decimal places, which is 1.512 for 3 marks. 42 then, let's have a look. Show that x1 is the value of beta correct to 3 decimal places. So this is one of the ones where we're going to be checking either side of our x1, and we're going to check the upper bound of that to 3 decimal places and the lower bound. And if the actual answer is that to 3 decimal places, then that means we're expecting a change of sign. So we're going to evaluate f of, well, the smallest number that we can have to 4 decimal places that would round to that is 1.5115, and we're going to work that out. And you should find that that is a very small negative number, 0. What have we got? 1, 2, 3, 397, which is negative. And then if we evaluate f of the biggest number that would round down to that, so 5125, okay, you should find that that is a very, very small positive number. Let's have a look, 0, 0, one more 0, 5, 6, which is positive. And then we say that stock sentence. You don't have to refer to the fact that this is a continuous function. It's kind of implied, but since there is a change of sign, actually no, that's not how I tend to word it. Change of sign, and I can't spell. Sign implies the presence of a root, i.e., so what that means, if there's a root between those 2 points, well, then that root is going to be 1.512 to 3 decimal places. Beta equals 1.512 to 3 decimal places. This does take for granted that we are dealing purely with continuous functions, but we definitely are dealing with continuous functions. And then the other thing they like to ask is, yeah, exactly this, why Newton-Raphson might fail. And you've got to think, well, the reason Newton-Raphson might fail, or one of the reasons it might fail, is because the derivative is equal to 0. And what that would mean if we went back up to look here, okay, if we went up to look here, we see that the derivative is in the denominator. We don't like dividing things by 0. So that would be the first thing I'd be thinking of, is evaluating f dash of x at the new point that they've given us, the new value they've given us, log of 3. E to the log of 3 is 3. And then you can see we're taking 3 away from that, so that is 0. Therefore, Newton-Raphson will fail. Okay, as soon as you get to the x value of a stationary point, Newton-Raphson is going to fall down. Okay, and I would want to show that amount of working because it's only 1 mark, but they're likely to say that you've got to convince them, because the answer is given to you. It says it does fail. You need to convince them that you understand why, and generally it's going to be because the derivative is 0 at that point. Moving on. So question 7, we've got a series question. The first and last term are that. So using the notation, you would probably say A equals -3 and L equals 61. The sum of all the terms is 957. Determine how many terms. Okay, so probably the least used formula, certainly when I teach this is the one I teach the least, is the one that's a plus L over 2 times n. So you're effectively, because this is a linear um, series or linear sequence, you're finding the average value and multiplying it by how many values there are in your sequence. So a plus L over 2 times n is another way of finding the sum of the first n terms, and we know most of those numbers here, don't we? We know a is -3, we know L is 61, and we know the 2, and we also know the sum, 9, 5, 7. So the average of -3 and 61, I believe, is 29. And so we've got 29 lots of n equals 9, 5, 7. And when you do that division, so 9, 5, 7 over 29, you get the answer of 33. Lovely. Moving on to the next part. Find the common difference. So yeah, you can do this in a couple of different ways. I suppose probably the easiest one, though, is noting that L is, of the last term, is the first term plus a bunch of common differences, and the number of common differences is one fewer than the number of terms you've got. So in this case, it's going to be 32 lots of the common difference because there are 33 terms. So I know that 61 equals -3 plus 32 lots of D. 32 lots of D will then be 64. D is 2. Okay, nice straightforward 2 marks there. I suspect there's probably another part of this question, so we'll move on. Here we are. Find the middle term. Yeah, I already talked about that when we were doing part A, didn't I? So it's going to be the mean average of the first and the last term. That negative is on top. There we go. So we have 29, and that is it. Okay. Now remember, this only works with arithmetic series and sequences because they go up or down by the same amount. It's not going to work if you've got a geometric one or one that's more complicated than that, like Fibonacci sequence or something like that. Okay, moving on to the next question. Oh, I remember this question. This did not go down very well. Yeah, the difficult part about this question is really beginning and figuring out what you've got to do and how you've got to do it. But once you get past that initial thought, really all you can actually do is try and factorize the top. Okay, and my recommendation for you would be, because this is a simplification question at the heart of it, not even at the heart of it, literally in the words, it's a simplify. So for it to simplify, one of these 3 factors, at least one of these 3 factors on the bottom, also needs to be a factor of the top. So that is where I would start. I would probably define f of x as the numerator, x to the 4 plus 5x cubed, minus 7x squared minus 29x plus 30. And I would try each one of those in turn. So if x minus 5 is a factor, then f of 5 will be 0. F of minus 5, sorry, will be 0. So let's do that, and you'll see that you get, what's that, 625 plus 625 minus 7 lots of 25 minus 29 lots of 5 plus 30. Okay, so I'll give you a second to work that out. You should see that that comes out as 0. So that means f of x, therefore, sorry, I should say up here, x plus 5 is a factor of f of x. Okay, so that means that x plus 5 multiplied by some cubic, so x cubed plus ax squared squared plus bx plus, well, I don't need to put plus c, I know what the c is, it's going to be 6. And I could work out what those a and b are and then do the same thing again. But actually, I'm going to go a little bit further because I suspect that at least one of the other two, the blue or the green factors, is also going to be, the numerator is also going to be a factor of the top. So I'm going to do f of minus 3. Oh, I just realized I made some sign errors, didn't I, above? So please forgive me for some of these sign errors. So let's fix those. So this is going to be minus 625. That's going to be positive. That's going to be negative, and now you get the 0. I must have typed something wrong in on my calculator. There we go. F of minus 3, so we're going to have 81 minus 5 times 27 minus 7 times 9 minus 29 times minus 3 plus 30. Let's see if I can use my calculator correctly this time. So I get there, I get another 0. So that's good. So I can say therefore x plus 3 is a factor of f of x. So now I can go even further. I can say that f of x is identical to x plus 5 from before, the x plus 3 that we just found multiplied by some kind of quadratic. So x squared plus, because I've used a and b before, I'm going to have to use a c here. And then the 5 times the 3 times what gives me 30? Well, it's going to be a 2. Okay, and now I'm going to go and do my comparing coefficients bit. I know that in my expansion, if I'm going to look at the x terms, I want minus 29 of them, and the places I get x's. In fact, no, I'm not going to do it this way. I'm going to go for broke and see if the third factor is actually there as well. So I'm going to try f of 2. Not in green, I'm not. F of 2. So then I'm going to get 16 minus 8 times 5 minus 7 times 4 minus 29 times 2. Oh, why have I got all these signs wrong now? That's going to be positive times 2 plus 30. And if I work that out, I also get a 0. Therefore, x minus 2 is a factor of f of x. Therefore, and this is really helpful, f of x is now identical to x plus 5, x plus 3, x minus 2, and then I know it's going to be x, and then I have to think 3 times 5 times minus 2 times what gives me 30. Well, 3 times 5 is 15, times minus 2 is minus 30, so that's going to give me a minus 1. Okay, so now my original function, if I go back and define it as g of x, I can say g of x is identical to x plus 5, x plus 3, x minus 2, x minus 1 over, and we already had the denominator, didn't we? 3 lots of x plus 5 times x plus 3 times x minus 2. If I use the colours from before, that factor and that factor go, this factor and this factor go, and then this factor and this factor go, leaving me with x minus 1 over 3, which is exactly what the original function g of x is the same as. Okay, so that's quite nice. It could have been made quite a bit harder if one of those 3 factors on the bottom wasn't there. We'd have had a bit more algebraic work to do, but it just came out quite nicely this time, and 5 marks, which is really nice. Okay, moving on to the next question. Right then, no prizes for guessing what this question is about. Proof by contradiction. So remember, with proof by contradiction, the essential gist of the question is you're going to assume the opposite of what they're trying to tell you is true, and then show that that leads you to some kind of contradiction, or show that that's a nonsensical statement. Okay, so we are going to assume for contradiction. You can leave that bit out if you want, but I like to put it for contradiction that there, handwriting on this is terrible, there are integers in mathy notation. There are x and y belonging to the set of integers such that 3x plus 15y equals 2. Okay. Now this is a little bit different from most of the ones that they've done before. If you've done my made-up paper from a few years ago, you'll see that actually I did one of these, and so I'm really happy to see it come up on a paper. I think my gut instinct, rather than messing about and trying to do any kind of substitution, I think the first thing I want to do is divide through by 3 on both sides, because what I'll do is it'll make the right-hand side, left-hand side, sorry, a little bit smaller for us, and it will give us 2/3 on the right. Oh, and actually, that is our contradiction. Okay, that cannot possibly be true if x is an integer, whole number. If y is an integer, it's a whole number, which means 5y is a whole number. So we've got whole number plus whole number equals fraction. And so there is our contradiction. So since x and y are integers, this means x plus 5y must be an integer as well, because when you add integers together, you get integers. And so yeah, there is our contradiction. Therefore, there are no integers for which 3x plus 15y equals 2. I mean, that's kind of common sense anyway, isn't it? You could look at that and think, well, the smallest integers you could use are the positive ones are 0 and 1, and no combination of zeros and ones are going to work. I suppose, yeah, when you go into the negatives, there's more combinations, but yeah, I'll stop waffling and move on to the next question. Okay, so here we want to sketch sec between 0 and, well, we're going to go up to pi by 2. So what you may want to do first of all is think, well, what does the cos graph look like for 0 to pi by 2? Pi by 2, remember, is the same as 90 degrees. So if I go in green here, the cos graph is going to look like that. In fact, I'm going to start again with these axes because I don't need negative y's. So if I look at that, the cos graph is going to start here at 1, and then it's going to decrease to 0 there. Okay, and that there is my alpha. And so the sec graph is going to be the reciprocal of that. So it's again going to start here at 1. Let's finish labeling my axes. It's going to start here at 1, and instead of decreasing, it's going to increase. What's going to happen then is at this value here, we're going to have an asymptote because we've got a 1 over 0. So we've got something that looks like that. Okay. And I've got my 0 there. Okay, the green graph, I would leave it there even in an exam, but do it in a different color to denote that it's not part of my answer. Okay, gonna move on then to part B. Okay, so I've got to explain why the integral of sec x between 0 and this alpha is greater than whatever alpha is. As you can see, I brought a little picture from the last slide with me. I'll just make it a bit bigger. So let's look at this graph. Now, it's not an integral that I'm going to be able to do very easily. Also, it's only worth 2 marks, so I know that's probably not going to be worth it. So let's look at this. There's one thing that jumps out at me is if I were to draw a little horizontal line there, the integral represents this area here, and then this area, I'll do that in a different color, and this area here. Okay. Now, what's really important to note about this area here is it's a rectangle, and it's a rectangle with base alpha and height 1. So the area of that is alpha. The important thing to note about this is there is a region that I've coloured in, which means the area here is greater than 0. Okay, which means that this integral is made up of 2 parts, one of which is the same as alpha, and the other one which is greater than or equal to 0. So we can say something like the rectangle has area alpha, the blue region has non-zero area, therefore the integral between 0 and alpha of sec of x dx is going to be greater than alpha because it's going to be the sum of alpha and something that's greater than 0. I like that question. Moving on. Right then, so immediately I'd like to think you look at this and go, I can't do that integral as it is. And when you get a complicated looking integral like this, your brain should then go, it's got to be partial fractions, especially when the denominator is factorized like that. So that's the first thing I'm going to do here. I'm going to say let f of x be equal to, and I'm going to write out the integrand. X plus 1 all squared, 2x minus 1. And I know that that's going to be the same as a over x plus 1 plus b over x plus 1 squared and c over 2x minus 1. Now, if you do them in a slightly different order to me, that's fine. Our a's and b's and c's will still end up being the same if we do it correctly, but in a slightly different order. So if you were to swap a and b, for instance, well, your a would be equal to my b. Okay, so there's no reason you absolutely have to do it like this. So then we're going to multiply through by the original denominator. So I'm going to get 5x plus 2 equals, well, when I multiply this first fraction here by the denominator, well, one of the factors of x plus 1 is going to cancel, and so I'm going to be left with the other one and 2x plus minus 1 as well. When I multiply this second term by the denominator, both of the factors of x plus 1 are going to cancel, so I'm just going to get b times 2x minus 1. And then finally this last term here, when I multiply it by the original denominator, the factor of 2x minus 1 cancels, so I'm going to have c times x plus 1 all squared. Lots of different ways to go from here, so it's really personal preference. I've always done it by substitution. definitely merits to comparing coefficients, but I've always done substitution. So I'm going to pick the number x is -1 to begin with, because that will cancel out my a and c terms. So I'm going to get -5 + 2, so -3. And then that is equal to -2 - 1, which is -3 lots of b. So b is 1. The other number that I'm going to choose is 1/2, because that will get rid of my a term and my b term. So I've got 1/2 + 1, which is 1.5. Oh no, let's deal with the left hand side first. So I've got 2.5 + 2, which is 4.5. And then on the right hand side, I've got 1/2 + 1, which is 3/2. When I square that, I'm going to get 9/4, which is 2.25 lots of c. So c is 2. Okay, and then it's this final step here where sometimes I use comparing coefficients, but still more often than not, I don't. I just use the simplest, smallest number that I haven't already used. Default is 0, but if that's already been used, I use 1, and then -1. So the left-hand side is going to be 2. The right-hand side now is going to be 1 times -1. So we're going to get minus a. Then we're going to get -1 lot of b, which is -1. And then we're going to get 1 lot of c, which is 2. So I think a should come out as -1. There you go. Okay, so what have we got there out of those 10? I would imagine normally 4 for partial fractions. So my original integral, and this is where I go back and become a little bit lazy, I'm going to call that integral I. I can say now that I is equal to the integral between 1 and 2, and now I'm going to write my function decomposed into partial fractions. So I'm going to have -1 over x plus 1, then 1 over x plus 1 squared, and then 2 over 2x minus 1, and that's all integrated with respect to x. Now I can see there's going to be a lot of logs going on here. So this terrible bracket. So this first one is going to be -1 times the natural log of x plus 1. I would include the mods here. I know everything is going to be positive, but I like to include the mods. Then this middle term here, I can definitely see some people making a mistake on this one. Remember, you should think of it as x plus 1 to the power -2. So you're going to add 1 to the power and divide by the new power. So you're going to get -1 over x plus 1. And then this last term, you're going to have 2 times the natural log of the bottom divided by the derivative of the bottom. So you're actually just going to get plus the natural log of 2x minus 1, because the 2 in the numerator cancels with the 2, which is the derivative of the denominator. And I can close my brackets, evaluating that between 1 and 2. So I'm going to get minus log of 3 minus 1 over 3 plus the natural log of 3. Take away, and then I'm going to put 1s in. So I've got the natural log of 2 minus 1 over 2 plus the natural log of 1, which is obviously 0. And they want the answer in exact form. Okay, so that's quite nice, because I can see that that term and that term are going to cancel. I'm going to have I missed out a negative, didn't I? There's a negative there. So I'm then going to get a natural log of 2 I just said that this term here is 0, and so I've got a half, take away a third, which is 1/6. Okay, and remember with questions like these, when they want them in exact form, that's obviously what you've got to do, but put the integral into your calculator to work it out and check that your exact form gives you the same answer as what pops out on your calculator. But I think that's a very nice 10 marker there. And moving on. Okay, on to question 12. Always one of my favorite questions. I've got absolutely no idea why I enjoy doing binomial expansion questions so much. They're always one of my favorites. So this function to me, immediately I think of it like this. Okay, now the common mistake is to look at that first term and think we have to do some kind of weird expansion with that, or when we're talking about the range of validity that plays any part, it doesn't. It's got a positive integer power, so the expansion, which is 2 minus x, is the same no matter what what number you put in. Okay, the approximation, well, it isn't really an approximation, so yeah, again, I'll stop waffling. So I'm only really going to concern myself with this bit. Okay, so let's have a look at 1 minus 2x to the power of minus 1/3. Well, that is approximately 1. And then I always put plus here, and I write down the power multiplied by minus 2x. Then hopefully you remember now that the pattern builds up. You take 1 off the power each time. And I can see I'm going to go over a line here, so bear with me 1 sec. Okay, there we go, that should be okay. And keen-eyed people might be able to see where I've dragged and dropped, but most people won't be able to. So I've got squared, and then divided by 2 factorial, and then the final term, I'm not going to go up any higher than x cubed, because if you look in the question, it says go up to x cubed. So minus 1/3, minus 4/3, minus 7/3, and unfortunately I'm going to go over the side here, minus 2x cubed over 3 factorial. Okay, or you can just straight away write 6 in if you want. Okay, so now for the evaluation bit. Obviously you've got a calculator here, so there is no sense in making mistakes by trying to do it in your head, but I am going to try and do it in my head. Plus 2/3 of x, and then in my next term I've got 1, 2, 3, 4 factors of 2 in the top and 1 in the bottom, so they're going to cancel, so I'm going to get 8 on the top, 9 on the bottom, and it's going to be positive, so 8/9 of x squared. Then the 6 on the bottom from the factorial isn't really going to cancel apart from with one of the factors of 2. So I'm going to have 4 times 4 times 7, which is 112, and then 3 times 3 times 3, which is 81, and again it's going to be positive. So I'm going to have 112 over 81 x cubed. Okay, I like to include here, no, I'm going to include at the end the range of validity. So I'm going to say then that that is f of x. So therefore, f of x is approximately equal to 2 minus x multiplied by that thing we just found, 2/3 of x plus 8/9 of x squared plus 112/81 of x cubed. Okay, so we've done lots of hard work. Let's not let ourselves down now by messing up the multiplication. So we're going to work out that term, that term, that term, and that term, because they're going to give us terms x cubed or less. Then we're going to work out that one, and that one. We don't need to do the fourth one here because it will be x to the power 4. So 2 4/3 of x plus 16/9 of x squared. plus 2 to 4 over 81 x cubed minus x minus 2/3 of x squared minus 8/9 of x cubed. And then when we tidy that up, we'll see we're just going to have a 2. 4/3 take away 1 is 1/3. 16/9 take away 2/3 is going to be 10/9 of x squared, and then 2 to 4 over 81 minus 8 over 9 is going to give us 152 over 81. There we are. And the bit that is forgotten so much because people are on autopilot and they don't remember to go back and read the question, find the range for which it's valid. Now remember, if you've got the product of two functions and then you find the expansion or approximation for that, the expansion is only valid for the more constricting of the two. So we know that this bit here is valid for all x, so we really only have to consider what this one is valid for. So we're going to say valid, we're going to try and spell it correctly, valid for mod x less than 1/2. You could first of all say the mod of 2x is less than 1 if you'd like, and then go to this as your answer. But that is my final answer, and there are 7 nice marks for us. Moving on. Okay, we've got some parametric curves here. Show that the gradient of the curve at the point where t equals p. That's how I always read that. I know it says where the parameter is p, but I always read that as where t equals p, and they give us the answer. So let's see if we can get there. Not in red. So we're going to start by dx by dt, differentiate that with respect to t. So we're going to have 6t squared dy by dt equals 6t. Therefore, dy by dx is dy by dt divided by dx by dt, or multiplied by 1 over dx, multiplied by 1 over dx by dt. Yeah, that's fine. So we're going to have 6t divided by 6t squared, which is 1 over t, at t equals p, dy by dx equals 1 over p, as we were asked to prove. Find the equation of the normal to the curve at the point where t equals 1. Okay, so remember we need two things. We need to know the coordinate of that point. So we've got the value of the parameter. We can now find the coordinate, and we also need to find the gradient of the normal. So we can work out straight away the gradient of the tangent, which is going to be 1 over 1, which is 1, and then that tells us that the gradient of the normal is going to be the negative reciprocal of that, which is 1. When t equals 1, x, y equals, well, when t is 1, I'm going to get 2 times 1 cubed plus 1, which is 3. And then for y, I'm going to get 3 times 1 squared, which is also 3. Okay, so we can then say equation is going to be y minus y1 equals mx minus x1. Okay, and that is sufficient for the marks, but if you wanted to write it in the form y equals mx plus c, you'd get y equals minus x plus 6, or x plus y equals 6, or x plus y minus 6 equals 0. Any of those forms are absolutely fine, but the penultimate line is sufficient to get you the 4 marks. Okay, moving on. I've just looked back to that back of that previous page. That was 8 marks in about 2 minutes. So these are very valuable as far as marks per minute go. Determine the equation of the tangent of the curve at the point where t equals 0. So let's do the same thing again. the gradient of the tangent is 1 over ODF. So that is undefined. Okay, now remember what types of lines have undefined gradients. It's vertical lines. Therefore, tangent is a vertical line. Okay, now the only thing you need to know about a vertical line, if I draw a little sketch here, if I were to draw my favorite vertical line here, the defining characteristic about it is where it crosses the x-axis. So every point on my favorite line there has the same x ordinate. So let's find out what x and y are when t equals 0. And if we go back, I think there'll be 1 and 0, won't they? 1 and 0. Therefore, the equation is x equals 1. Okay, because if one point on the line has an x ordinate of 1, they all must. Okay, so the equation of the line is just x equals 1. Okay, y could be anything. Okay, lovely. Moving on. And it surprises me that we've got to question 14 before seeing integration by parts. But looking at this one, I don't know if it's a dead giveaway to everybody, but the fact that we've got an x squared in there means we're going to have to do it twice. Now, I've always thought that these questions, they're not difficult. This is just a test of your notation and your ability to work nice and neatly. So I'm hopefully going to show you how I would do it nice and neatly. So I is equal to, but first I'm going to go over here and I'm going to write down u, v, du, and dv. Okay, now remember, 9 times out of 10, your u is going to be your polynomial, particularly when your other function is a trig function. You're almost never going to choose your trig function as your u. So that means I've got x squared here, which means I've got 2x dx. This is a bit too squished. I'm going to write this out and start again. So I've got u is 2x. No, it isn't. X squared. Du is 2x dx. Dv is going to be cos x dx, which means v is going to be, well, the integral of cos is sine x. So there's me banging on about notation and making it look nice, and I've gone off the page straight away, but there we are. So the integration by parts formula, remember, is uv minus the integral of v du. So I'm going to have x squared sine x minus the integral between 0 and pi by 2 of v du, which is going to be 2x sine x dx. Okay, some of you might be there sitting there shouting, well, what about the first term? Where have the limits gone? And you're right, I do need to consider that. Now, it is entirely up to you when you use those limits, when you sub them in. You can save them all to the end and do it all in one hit, or you can do it as you're going through. Personally, I prefer to do it as we're going through. Okay, so now for this first term, I'm going to sub in pi by 2. Okay, so when you sub in pi by 2 into sine of x, well, that's 90 degrees, so sine of x is 1, which means this is just going to be pi squared over 4, and then you're going to subtract what you get when you put 0 in, so I'm going to have 0 times 0, which means I've got nothing. Okay, so that's a lot easier to write than those big square brackets for stuff in. Minus, I most of the time choose to take the numerical factors out, okay, leaving me with just x sine x dx. And remember the rules for integration by parts. The whole point is that the integral, the second integral you write down, is easier than what you started with. And here it definitely is, because the power of x has gone down by 1. Okay, so that it may not look much easier, but it is easier. So we're going to go through the process again. U equals x, du equals dx. which means dv is everything that's left, which is sine of x dx, and so v is minus cos of x. So I can go through and do my second round of integration by parts. So I've got that there, minus 2 times, and then I've got uv again, so minus x cos x, again evaluated between 0 and pi by 2, minus the integral of v du. So I kind of want to write minus cos x dx in the integral, but I'm going to absorb that minus and change that to a plus. So 0 pi by 2, and then this is just cos of x dx. Okay, and again, the rule is what is my now third integral easier than my second, which was then easier than my first? And the answer is yes. Okay, so let's keep going. Pi squared over 4 plus 2 lots of x cos x between 0 and pi by 2. Hopefully everybody noticed that I absorbed this minus into this one to make that plus there. And then finally, I've got minus 2 lots of the integral between 0 and pi by 2 of cos x dx. And we're finally now at a point where we can evaluate that integral straight off. Okay, so I'm going to do a couple of things on this next step. I'm going to evaluate that set of square brackets. So when you put pi by 2 in, you'll get pi by 2 times 0. Lovely. And then when you put 0 in, you're going to have 0 times 1, which again is 0. So that whole term goes away. Okay. And then I've got minus 2 times that integral. Now the integral of cos, I don't know if you remember, but we did it back up here in the blue. The integral of cos is sine. So I've now got sine of x between 0 and pi by 2. And so finally, I think we can write down our answer. When I put pi by 2 in, I'm going to get a 1. And when I put 0 in, I'm going to get a 0. So this is going to be minus 2 times 1 minus 0. So my answer is that. Okay, and it does say exact, so I can't really faff about too much with this on the calculator. But if you are like me and you prefer things written as a single fraction, you could do that. Okay, which I think is a really nice looking answer to this question. Okay, so hopefully you can see it's just a matter of being methodical, going through it nice and slowly, not rushing. And I do like the little U's and V's and stuff. You can see I've used a different color. I would do that in an exam, or do it in pencil, or do it on a separate bit of paper. Well, not a separate bit of paper, off to the right in a different color, just so for my own benefit more than anything else. Okay, moving on to part B. I think integration by substitution might be every student's favorite type of question. Even the ones where they give you the substitution, I know people don't like them very much. So again, I'm going to call my original integral I. I've been given the substitution, and I should then pretty much just go into autopilot. I know that I'm going to differentiate that with respect to x and see what I get. Derivative of 1 is 0, derivative of natural log of x is 1 over x. And what I can see in my integrand really nicely is I've got a 1 over x times dx. So I'm going to rearrange this one to say du equals 1 over x dx, and I'm going to color it in yellow to show you that that bit, that is going to get swapped in instead of the yellow bit. The original substitution that we were given is that bit there, and I'm going to swap that instead of u. And then the only problem remains is I've got this bit here, apparently the word an, There we go. I've got that bit there. Now, not really a problem if you think about it, because what you can do is you can rearrange the original substitution to say that the natural log of x is equal to u minus 1. Okay, and so what I'm going to do is I'm going to swap that in place of the blue bit. Okay, so you can see I've used 3 colours here. That's probably the most you're ever going to need to use for the integrand. You may need up to 1 more colour if they give you limits. So I would use my red highlighter if there were also limits to change the limits from the x world into the u world. Okay, so I can now rewrite my integral without any x's at all. Every x is going to turn into some function of u. So let's start with the blue one. I'm going to swap that for u minus 1. I'm going to have a fraction. Let's do the green one next. So I've got u squared, and then the 2 yellow bits, which I think is the hardest bit actually. I think that's what would catch lots of people out. I'm just going to write that as du. Okay, so probably a couple of marks out of the 5 gained there. We're not out of the woods yet because there's still plenty of places for people to go wrong. The amount of times people have tried to do some kind of integration quotient rule on stuff like this and then got in all kinds of bother. It's actually much, much easier than that. Break this up into 2 separate fractions, like that, and then each one is nice and straightforward for you to integrate. So u over u squared is 1 over u, which is u to the minus 1. And then 1 over u squared is u to the minus 2. So minus u to the minus 2 du. And then we can integrate this, hopefully no problem. When you integrate u to the minus 1 or 1 over u, you get natural log of mod of u. When you integrate u to the minus 2, you add 1 to the power, divide by the new power. So you should, in this case, get plus 1 over u plus, I think this is the first time I've used a constant of integration. I didn't have to use one on the last question because we had limits. And so the only thing that's stopping us from finishing there is my original integral was a function in terms of x, so my final answer is going to be 1 in terms of x. So let's undo our original substitution. Wherever we see u, we're going to put 1 plus log of u. So we've got the natural log of 1 plus the natural log of x plus 1 over 1 plus the natural log. I don't need the mods, do I? Of x plus c. And there's our answer. Here we are. Move on to, I think, question 15. Yeah, moving on. Okay, 2 crowd favorites in a row. So integration by substitution followed by functions. So looking at this one, you should kind of know-ish what this function will look like, because 9 over x minus 3 all squared kind of looks like that. If you think about it, I know there are some differences. The 9 makes a difference in terms of the steepness. The minus 3 makes a difference in terms of a horizontal shift. But really, in the grand scheme of things, it kind of looks like that function. And you should know that that function looks like this. Okay, and you can see that each one of those 2 parts is a 1-to-1 function. All that will have happened to get to the one that we've got is it will have been made steeper because of the 9, and it will have been moved 3 to the right because of the minus 3, which means the asymptote that's on my diagram at 0 will be at 3. So whereas you may have not paid any attention to this piece of information right at the start, you can now see that it's really important because it's telling you you're only looking at the right hand of the 2 parts of this graph. And the reason I talk about that for a minute and a half is because if you know you're only looking at one part of these, it's a 1-to-1 function. And if it is a 1-to-1 function, you know you can use the endpoints of the domain to find out what the range is. Okay, and we know that the domain of f in this case is 3 all the way up to infinity, which means the range of f, well, the endpoints are going to come from that 3 and from that infinity. Okay, so if we think about what happens when we make x very, 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 very big, well, when you take some 3 off it, it's still going to be very big. Square it, it's going to be very, very big. And then when you do 9 divided by something astronomically big, it's going to go towards 0. Okay. The converse then, when you try to use the 3, when you put numbers that are approaching 3, so 3.1, 3.01, 3.001, and you can try this on your calculator, you will see that the denominator is getting much, much smaller. Then when you square it, it gets even smaller again. And when you divide 9 by something that's getting smaller and smaller and smaller, it will fly off up to infinity. And those are both strict brackets. You can never attain the infinity. Also, you can never get exactly 0. Okay, and so there is our range. Moving on to part B. Find an expression for f inverse. Now, if you wanted to be really sneaky about it, all that talking I was doing about one-to-one functions and drawing the graph and thinking about it, if you'd have just scanned ahead to part B, because they're asking us to work with the inverse function, that means the function we had originally on the domain that was given to us must be one-to-one. So you could have cut out all of that thinking that I was doing and just looked and said, oh, it's something to do with the inverse, which means it must be a one-to-one function. And then work out the endpoints like I did. So looking at this one, we're going to say y equals, and we're going to set it equal to our original function. Now we're going to have to bear in mind here that because there's a square in our original function, that means there's going to be a square root in our inverse. If there's a square root, that means there's a plus minus. So we are going to have to justify our choice of sign here. I imagine 4 marks out of these 5 are for the manipulation. 1 is for some justification. Okay, and so it's worth remembering that because the domain of the function is 3 or greater, that means positive, that means the range of the inverse function is 3 to infinity. So this function can only output positive numbers. That might be important in a minute. Multiply both sides by x minus 3 all squared and divide both sides by y. Take the square root, remember the plus minus. Okay, I'm not going to do anything with that plus minus just yet. I'm going to save it for a little bit later. X then equals 3 plus or minus 3 over root y. Okay, and then what I can do is I can say this is where the fact that I talked about a minute ago, this bit here, where this becomes important. If I were to take the minus, for instance, and if y was very, very small, then I would have 3 take away something bigger than 3, which would be negative. So since the range of f inverse is greater than 3, we ignore the negative. Okay, so I can then say, therefore, the inverse function of x is going to be equal to 3 plus 3 over root x. Okay, but that justification up here is important. I suspect you'd only get 4 out of 5 if you left that out. Also, do not forget the plus minus. Yeah. Moving on to, I suspect, a part C. Oh, no, I was wrong. Question 16. Oh, I remember this one. So a little bit of a caveat here. I know a lot of people don't like the way that I've done it. there is a slightly different way in the mark scheme from how I do it. So if you don't like my way, and I know there's a lot of people who won't, please look at the mark scheme. Okay, so let me try and set this out clearly. The way I personally prefer to think about this is I prefer to think of being at the point where I've just paid my last payment off and I owe nothing left on this loan, and um, building up and writing down what happened, how much money I paid, and what happened to that money at every single step. So I'm sort of looking at the bank statement really and saying, right, I paid this, and this amount of interest was accrued on it. Um, and I think it may be just easier if I start. So I'm at the point now where I've paid everything off. If I look back and I think about that very first installment that I paid, so I'm going to call that installment. Have they told me which letter to use? Each installment is paid after the interest has been added. Calculate the amount. So let P equal the annual, and you can't spell annual payment. Okay. And so what I'm going to do is I'm going to effectively be looking at what happens to each of my payments. So I'm going to pay a payment in, okay, and then that is going to be increased by 5%. Then I'm going to add another payment in. This is the next year now, and then all of that is going to be increased by 5%, because the first set of installments that I paid are worth more effectively. And then the same thing's going to happen again. And you can hopefully see where this is going. I'm just going to keep having this nest of adding an installment, multiplying by 105%. Okay. And if you think I'm going to have 20 of these P's added in, and each time I add a P in, I multiply by 1.05. So this initial P here is acted upon by all of the 1.05s, all of the interest is put onto that. So if I were to expand all of this and collect like terms, I'm going to have P times 1.05, and there's going to be 1, 2, 3, 4, and there's going to be all of them. So I'm going to have 20 applied to that. The second P, and I'm not going to be able to do this for all of them because I haven't got enough colours, that is affected by all of the 1.05s apart from the very first one. Okay, so there's going to be 19 of those, and then the next one is going to be 18, and so on, and so on, and so on. Okay, looking back, I've miscounted how many interests are on each one. This here should be a 19, and then so everything I said was right apart from how many of them there are. P times 0.05 to the 17 until you get all the way down, and the very final payment you make does not have any interest. Is not affected by any of these interests, any of the interest. Okay, and so if you look at that, hopefully now you can more clearly see that there's a GP, a geometric series at work here. So we could say that this is a GP where the initial term, the first term is P, the common ratio is 1.05 and there are 20 terms. Okay, so we need for the sum of those 20 terms to be equal to the amount that we borrowed. Okay, because if it isn't, once you've made the 20 payments, you'll be thinking, oh, I finished, but actually you still owe them some money, so that's not an ideal situation. So we need that S20 is equal to 50,000. Okay, and remember the sum of the first 20 terms of a GP is going to be, well, you've got the formula in your formula booklet, A times 1 minus R to the N over 1 minus R, and so that's got to be equal to 50,000. Okay, so P is equal to 50,000 times 1 minus 1.05, and yes, I know we could work that out if we wanted to. 1 minus 1.05 to the power of 20. And if you put all of that into your calculator, you should get that the annual payment needed is £4,012.13. Okay. If you were to do it any of the other way, you are still doing all of the same maths. You're just looking at the same problem, possibly from the opposite end to what I am, but hopefully what I've just done there makes sense for you guys. And I'm pretty sure that that is the end of the paper. So yeah, we've just got this page for some extra working if we want, but we don't need to do any extra working. Okay, so thank you very much. Hope you found this useful.